it says that if you have the derivative of f of g of x, then the derivative is going to be the derivative of the outside function. So it's f prime of the derivative of the outside function evaluated at the inner function times that by the derivative of the inside function times g prime of x. Okay? Now, if you have an antiderivative that has this as the integrand, you're assume you're taking the antiderivative of this thing. So in the integrand, you see, this is what you see. You see some function times some function that has an inner function. Oh, and it also has the derivative. Okay, so assume this is, and I'm not going to write the prime here. So imagine that your antiderivative involves this integrand of what you have is, first of all, a factor that is composite. At the same time, I'm going to show you guys an example. Let's say the antiderivative of the square root of, let's say that the square root is the outer function. And assume that within the square root, you have x squared plus 1. So f is the square root. G of x is inside the square root. And then outside of the square root, within the integrand, you have the derivative of the inside part. So here, let's say we have a 2x sitting. Then we know that we can do the opposite of the chain rule. If the antiderivative is in the form, in this form, then substitution can be done. Okay, so how can you do the substitution? What we're going to do is we're going to let u, it's typically the variable u that you use, let u equal to the inner function, let u equal to g of x. Okay, so for instance, for this example, I'm going to let u equal to x squared plus 1. Okay, so the function becomes the integral of f of u. Okay, now what you also do is take the derivative of this, because we have a dx, we have a derivative of g prime. Take the derivative of this relation. So you just do du dx, differentiate with respect to x, that gives you g prime of x. And this, we call this the derivative relation. This is the derivative, this is the actual relation, this is the derivative relation. What you do next is multiply both sides of this thing by dx. You're going to get du equal to g prime of x dx. Okay, so if I do that here, du dx, the derivative of u with respect to x, is just 2x. multiplied by dx, you get du equal to 2x dx. And if you don't mind, I'm going to write that dx in green. Okay, so what you substitute for this factor here is simply du. Okay, this whole thing becomes du. Okay, so if I were to rewrite this antiderivative, it's going to be the antiderivative of the square root of u, and then that 2x dx here is simply du. So what happened here is, or what happens here is that this integral or antiderivative transforms to an easier antiderivative. Look at that. We can do this antiderivative using the power rule fairly simply, right? This is just, it's just that the variable has changed. That's all. We did a transformation on the antiderivative. This is the same as saying the integral of u to the half du. Okay, so you do this integration using the power rule. Add 1 to the power, you get u to the power of 3/2 multiplied by 2/3. Don't forget the constant of integration. Okay, we just evaluated the antiderivative in terms of u. So if I write this, the general form, the antiderivative, let's call it capital F of u. Capital F, remember, stands for the antiderivative plus c. And then the very last thing that you have to do is replace u back with what it already was. U is the same as x squared plus 1. We have to replace back because the original problem is in terms of x. So you got 2/3 times x squared plus 1 to the power of 3/2 plus c. Okay, so in the end, here f is the antiderivative, evaluate that at whatever u was, use g of x. I really hope that makes sense. I really do. The colors here, I hope help, but
what's the whole point of finding the derivative of the inside if it's just going to be substituted by dy dx anyways? I mean du dx.
I got you. So, okay, I got you. So you're saying, but what's the point of doing all this?
Yeah, if you're not going to use the 2x at all.
You know, well, we are not using the 2x. The 2x has to be here. If the 2x wasn't here, could you have done the problem? Like, imagine if this is not there.
Oh, no.
I wouldn't be able to do the problem, right? Because I need to, when you do substitution, you have to transform everything. So if the 2x wasn't here, then what would you have replaced dx with? Dx would have been, if you solve for dx would have been du divided by 2x. And that's just gonna look really weird. We need this. We need the, if you look at the original form, we need the derivative of the inner part sitting outside, because if you don't have that, then this is not chain rule. We're not doing the opposite of chain rule. So the derivative of the inner function, guys, the derivative of g of x has to be sitting there in the integral, else we just can't answer the question at all. That's why I'm telling you, finding antiderivative is not easy. If I didn't have this x, I wouldn't be able to do this problem. There is nothing to substitute for that.
So you continue with the outside function all the way to the bottom until you
yeah,
close
but
out.
again, if we didn't have this x, at least if I didn't have that, then what would I substitute for my du? You know what I mean?
Yeah.
Yeah, so it has to be sitting there. When we do substitution, you look at two things. Do we have a composite function? Okay, so yes. I look at that, I see the square root of x squared plus 1. This is composite, so great. Next question you ask yourself is the derivative of the inside function sitting outside of the composite function? So you look at the inner function, its derivative is 2x. I see that right here. Then I can go ahead and do substitution rule. This is called a U-sub. Or the integrand must involve a composite function and the derivative of the inner function must be a factor of the integrand. If you guys don't know what an integrand is, this is the integrand. This whole thing, what you take the antiderivative of is the integrand. So here we have that the derivative of the inner function. Let me just highlight this. Okay, and we also again have to have a composite function. Okay, so again, look at the integrand. Do you have composite? Yes, this is composite because again, I read that as a square root of the word of means the composite x squared plus 1. Okay, that checks out. X squared plus 1 is the inner function. I look at that, the derivative, I calculate the derivative of this in my head. It's 2x. There is 2x. You can do substitution. Okay, so what you do is you call u to be that. You also find your du and then substitute. Use that and that to substitute. This u goes for the inner function, and this 2x dx goes for du. You replace that whole thing with du. All right, I really hope that you guys say as simple as that. I really hope. Now, what if I don't have this 2x? So you could, by the way, you can look at this a little bit differently. Let me show you something else. Let me just redo the problem. You can look at it this way also. You can begin by letting the inner function to be u. Okay, so let u equal to x squared plus 1. And begin transforming your integral. You get the square root of u. Okay? And then when you do these problems, you have to substitute for two things. You have to substitute for that inner function, and you have to also substitute for your dx. So in this situation, let me actually write that dx in red. Yes, you must also substitute for dx. So look at this relation. Use this relation to calculate dx. So what you do is take the derivative again, du dx is equal to 2x. Multiply both sides by dx to get rid of a fraction. Now, since I have to also transform this dx, I have to make this in terms of u, then I look at this relation and I solve this relation for dx. You can solve this for dx. Dx is equal to du divided by 2x. Okay, so you're gonna stick that for dx over here. 2x is already there. Dx becomes du divided by 2x. And as you see here, the 2x's cancel out. So what you're left with is, again, the antiderivative of u du. See how that worked out? Your antiderivative turned into something that you can actually do. So you go ahead and finish same way as before. Okay? Now, what if let's modify this problem a little bit and try to answer it. What if this constant factor of 2 wasn't there? Well, let's see what happens. This 2 is just, guys, the 2 here is just a constant, and we can always manipulate constants. We can factor them, divide them, get rid of them. We can do all of that stuff. So let's just redo the problem without having that 2x. So x squared plus 1 times, let's just say x dx. So which method did you guys better? Did you guys like the direct method or this way? First or second?
The direct method?
This better?
Yeah.
Okay. All right. So, all right. Again, I look at an antiderivative. I ask myself the following: Do I have a composite function? Yes. Is the derivative of the inner function sitting there in the integrand? So the derivative of that is 2x dx, or it's just 2x. Well, I don't see a 2 here, do I? I don't see a 2. But I can always force there to be a 2. I could always put a 2 here. I could put a 2 here, divide by a 2. You know what I mean? The 2 is not a problem. You could create a constant. You can always do that. So as long as I have x, the derivative of that without the 2, without the constant. So if this was a, yeah, as long as I have the derivative of that, of the inner function without the coefficient, I'm all good. It's just gonna work out. So we're gonna let u equal to, again, x squared plus 1. Okay, so while you're at it, do du is equal to, so it's du dx again. It's equal to 2x multiplied by dx. You get du equal to 2x dx. Okay, so I look at my integral, I see that there is an x dx. I look at this relation, I see that there is an x dx right there. So what I do here is I solve for this x dx by dividing this relation by 2. X dx is equal to 1/2 du. Okay, so substitute now. You're going to get the antiderivative of the square root of x squared plus 1 is now u. And then this x dx is 1/2 du. Y'all see how that worked out? So why is this okay? Because 1/2 is just a constant. I can take the 1/2 out of the integral and do the integral. 1/2 out, you have the antiderivative of, again, u to the power of 1/2 du. So keep the 1/2, it's a constant, and do the antiderivative of u to the half. At 1 to the power, you get 3/2. Multiply the result by the opposite, 2/3 plus the constant. I can get rid of those 2's. I end up with 1/3 u to the power of 3/2 plus c. And again, don't forget to substitute back. 1/3 u here is x squared plus 1 to the power of 3/2 plus the constant. Again, guys, without this x here, we just can't do the problem. We really can't. Because when you look at the derivative, when you take the, when you do du dx, this du dx involves an x. Right? I need to have an x dx to call that, to be able to write the du over here. Just not gonna work. All right, so let's do a lot of problems because substitution rule is just so important. And if you don't know this method, again, you're not gonna be able to begin Math 8. Okay, so examples. Let's say this was example 2. Let's just do a bunch of problems out of the book. So let's go with the antiderivative of, let's say, x squared cosine of x cubed. And I'm just going to use colors here. Well, the colors kind of give it away here, but it should help though. Okay, so here we got an antiderivative. First of all, guys, please try and think simple. If you can do the antiderivative without using the substitution rule, if it's a basic antiderivative, then just do it that way. But I don't have antiderivative of cosine x by itself. Okay, this is not an elementary antiderivative because it involves a composite function right there. How do you read this? X squared times. So x squared is a factor. It's a factor. Times cosine of x cubed. Of x cubed is the inner function. You got yourself a composite function right there. So question is, can we use the substitution rule? Try to make that determination in your head before trying the rule, because it might not work out. So I asked myself, so first, the first requirement is met. I have a composite function right there. Now, second requirement is this. If it is the derivative of the inner function sitting as a factor of the integrand, this is the factor of the integrand, the derivative of x cubed is 3x squared. X squared. Yes, I know it's a 3x squared, the derivative of x cubed, but again, the 3 is just a constant. You can manipulate that. So we can use substitution. Okay, let u equal to x cubed. Do du. Du is equal to 3x squared. So that's just du dx. Dx is 3x squared. Multiply by dx. You get du equal to 3x squared dx. You can skip this step if you want and just say this is the derivative of that du, and then here 3x squared, just put the dx here already. Okay, so I'm looking at this and I see my x squared dx. There is your x squared dx. I can solve this relation for x squared dx and plug for that. All I got to do is divide by 3. 1/3 du is equal to x squared dx. Okay, so now we substitute. This is equal to, here, let me do that thing. So this right here is 1/3 du, and this guy is just u. So the integral now transforms to 1/3. 1/3 is a constant factor that you can take out of the antiderivative by the rules of antiderivatives. So I'm going to write the 1/3 out. Times the antiderivative of cosine of just u. Okay, du. Okay, so there's this 1/3 du is right there, 1/3 du. And then here you have the cosine of u. This is an elementary antiderivative. The whole purpose of doing substitution is to transform the antiderivative into something that we can actually do. Convert to a basic antiderivative, and we can do that antiderivative. With the 1/3 sitting out, the antiderivative of cosine of u is sine of u. It's not negative sign, but it's just sine. You don't need the parentheses. Don't forget the constant, and then you can replace u back with x cubed. So you get sine of x cubed. You could put the parentheses, don't put it, doesn't matter. Plus c, and that's the answer. Okay. Questions? All right. want to show you guys something cool. I don't know if it's cool, really. But let's go with this antiderivative. X plus 1 squared. So I took a step backward, going with something easier. Okay. So how would we do this problem? How would you approach this problem if you didn't know the substitution rule? Anybody?
We have to expand it first.
Yes. Yeah. If they ask you this question in the last section, you would just square x plus 1 and do the antiderivative term by term. Well, you can do that. Let's do it that way. This is equal to, so this is the direct method. It's the antiderivative of x squared plus 2x plus 1. And then integrate term by term. You end up with 1/3 x cubed plus just x squared. The antiderivative of x is x squared over 2. The 2's cancel. And then the antiderivative of 1 with respect to x is x plus some constant. So pretty quick. This is fine if you did it this way. Okay, so this is the direct method. Now, the alternative method is for you to do a U sub. The U sub is better. It's easier because if this was a power of 4 or 3 or 10, then doing the algebra, expanding it is not easy. Okay, so let's do substitution instead. We're gonna let u equal to x plus 1. Okay, so that's great. And then du, if you do du, just do du dx. The derivative here is just equal to 1. And multiply by dx to get rid of this fraction, the denominator, which is dx, you get du equal to just dx. 1 times dx cancels that out. So substitute now. You end up with the integral of just wait, why is that a cube, guys? I'm sorry, that's a square. That was supposed to be a square. That's a square.
Professor, du or dx, the original function?
And that should be a dx. Yes. You can't have antiderivative of something that involves x with respect to u. It just doesn't make sense. So yeah, basically same problem. I'm doing the same problem substitution method. So we get the antiderivative of u squared. Dx is just du. There's no craziness going on where you have to divide or. So you just get du. And we all know the antiderivative of u squared. It's 1/3 u cubed plus c. And then substituting back, you get 1/3 times u is x plus 1. So this is the answer. Okay, I'm done right there. You would abandon the problem. You're done. Okay, now, here is the thing. So why am I doing this actually? Why did I do it both ways for you guys? Because Well, you know what you guys do typically? You go to the back of the book to check your answer, okay? Or you use PhotoMath or MathWays, one of those applications. Take a picture of the problem. You don't even bother writing down, typing the problem. But they give you an answer, okay? So you look at your answer. This is your answer, let's say. And you look at Book's answer. Let's say this is Book's answer. Well, they're not the same, of course, because this is not expanded. So you're like, okay, maybe I should cube this to check and see if it's consistent with what we have here. All right, so let's do that. Let's cube this thing and see if it's the same. If I cube x plus 1, again, you can use that Pascal triangle thing. You get x cubed plus 3x squared plus 3x plus 1 plus c. Okay? Or you could just multiply x plus 1 by itself 3 times. That's what you get. Then you multiply the 1/3 in. You get 1/3 x cubed. Now this 1/3 multiplied by these two, those 3's will cancel. You get plus x squared plus x plus 1/3 plus c. Okay, so that's the answer I got. I'm not gonna box it yet. Let's say I did the problem this way. I did substitution method. I got this as the answer. I compare to the back of the book. And this is an expanded form. So I expand, this is what I get. Now I'm gonna compare that to the back of the book. Okay, I got the 1/3 x cubed. Great. I got the x squared. Fine. I got the x. Where the heck is my 1/3? I'm asking. What happened to 1/3? Why does this not have a 1/3, but this has a 1/3? Anybody?
Is 1/3 just a c?
Yeah. Yes. Thank you. 1/3 is a constant. Okay. So is c. Do I know what c is? No, I don't care. It's just a constant of integration. It could be anything. Okay. If I combine this constant with this constant, I get another constant. You could call it whatever, C1. So when you combine these two, you can just express that combination as a single constant. Now the answers are gonna match. Plus, call it C1. Where here C1 is 1/3 plus C. Okay, these constants, guys, these constants are not the same constant. It's just a constant. We don't know what it is. We don't get it could be anything. But we know that if I combine a constant with a constant, I get a constant. You could still call the C if you want. Now the answers do match, don't they? So expect that to happen when you are when you do an antiderivative on your own and someone else does it on their own. It is likely that you guys get different answers, but actually the same answer but in different forms. That could happen. Okay. That's why a lot of the students who do the homework, they kind of get stuck. They keep checking and rechecking their answer when they compare theirs to the back of the book, and they just can't find anything wrong with their work. So if that happens to you, keep in mind that different methods of finding antiderivative can give you different looking can give you the same answer, but in different format. Okay, that can happen. Just letting you know. Okay. All right. Let's do a couple of more. So again, if this was a power 10, you definitely want to do, if this is high power, then you definitely want to do substitution, because raising this to powers that are more than 3 is kind of difficult. Substitution is a better way to go. Okay, let's look at a couple of more easy antiderivatives. Let's say I am to find the antiderivative of sine of 2x. That's sine of 2x dx, or it could be sine of 3x dx. So here I have a composite function because that reads as sine of 2x. Okay, I got the composite. Now, next thing is that if I let u equal to 2x is the derivative sitting in the integrand, well, the derivative of 2x is just 2. It's simply 2. And 2 is a constant you can move, you could manipulate. So substitution is just going to work out. Now, if you can't check the requirements and all that stuff, you can just go ahead and try substitution to see if it works. Just do the math. By letting u equal to 2x, so you right away do du dx. That gives me just 2. I multiply by dx, I get 2 dx. So I see again, there is a dx. I can solve for this dx. I get 1/2 du equal to dx. Now we are ready to substitute. So you're going to use this and this to substitute for the inner function as well as the dx. This transforms to the antiderivative of the sine of u, and that dx is 1/2 du. You could have just begun by moving the half out of the integral. You could just skip that step and write the half out. Okay, now we all know what the antiderivative of sine is. Antiderivative of sine of u is just, well, it's negative cosine of u. With the half sitting out, I get negative cosine u plus c. You can leave the c in the bracket, out of the bracket. It doesn't make any difference. If I left c within the bracket here, then half times c is another c, so who cares where you leave the c? Okay, so substituting back for u, we're going to get negative 1/2 cosine of u here is 2x plus c. Okay. Now, I want you with these problems, I want you just to skip the u substitution, to be honest with you. So if you look at this antiderivative, the final answer, first of all, we just take the antiderivative of sine, which is negative cosine. And then there is always gonna be a 1 divided by whatever the coefficient of x is. The coefficient of x is 2, so we're always gonna have a 1 over 2 in front. And again, the 1/2 comes from the dx part, okay? So you can always use this rule, always. You don't even have to do a u sub. I'm allowing you to, anytime you see the antiderivative of sine of ax, so for our example, a was 2. Anytime you see that, the answer is right away -1 over a cosine of ax plus some constant. So if this was a 3x, you end up with -1/3 in front. Okay, same goes for cosine. The antiderivative of cosine of ax is 1 over a. The antiderivative of cosine is sine. Okay, and in general, the antiderivative of f of ax is, by substitution, is always gonna be 1 over a times capital F of ax, where capital F is the antiderivative of the little f. Okay, this is always gonna hold true, so you can just skip u substitution if you want. It's up to you, or just do the u substitution. Any questions so far?
Professor,
Yes.
this is correct when we don't have the constant in the given question, yes?
Is it true what? If you don't have the constant in a given question?
Yeah, the constant of derivative inner function.
Well, what do you mean? I don't understand your question though. Like, give me an example.
So here is the derivative of 2x is true. We don't have to here.
Where?
5 in front
Right.
of,
So you don't have 2 here
yes,
outside?
yes.
Well, I got you. So that's why there's a 1/2 in. So when you do the u sub, u is equal to 2x. Remember what I said about constants? You can manipulate. Look at this. I could divide it out. So when I do du is equal to 2 dx, right?
Yes.
So I could, since I don't have a 2 in front, I can divide that 2 out and get 1/2.
No, my mean is when we don't have constant, so we can use this formula that you gave us.
These formulas?
Yes.
When you have a constant or when you don't have a constant?
When we don't have constant.
Yes, you can. I mean, yeah, for sure. So if you didn't have the a in front?
Yes.
Yeah. If you didn't have if a was just 1, then here you get 1 over 1 cosine x. The antiderivative of sine x is negative cosine x, right? Yeah, you can. Of course you can. These formulas work all the time.
Thank you.
But this has to be, yeah. This can't be a variable though. This can't be like an x squared or a square root x. It has to be. Is that what you mean? Are you asking, what if this is only just a 1?
No, Professor. I ask you because in the function that you give us in the example 5, we don't have the derivative of 2x. in front of function, yes?
You're right, we don't.
So if we have a derivative, we don't need to use this formula.
Right,
Yes?
yeah. Okay, now I understand your question. Exactly, you don't. You don't, absolutely. Even if you had that constant, you can still use these. It's just gonna work out. But yeah, if there is a 2 here already, then you know that the derivative of 2x is 2 dx. Yeah, so the answer to your question is yes.
Thank you.
Always. Okay, now let's do a lot more complex problems. Let me choose a bunch of problems out of your book. And let's do some that actually are definite integrals that go from a number to another number. Okay, so let's go with problem. Problem number, what would be a good problem? So example 6, or is it, yes, 6. The definite integral, so this is not just an antiderivative, this is a definite integral that goes from 0 to pi over 2. And it's cosine of x times sine of, again, read the problem out, loud. Sine of sine x. It looks like a really ugly problem. It does. But again, cosine times sine of sine x. So I can see that there's a composite function right there. That inner sine x is the inner function. I'm trying to switch the color here. Okay, and then the cosine x dx, that's the outside factor. So you ask yourself, if I let u equal to sine of x, the inner part, is the derivative sitting on the outside? The derivative of sine x is cosine x, and it's sitting right there, so we can do substitution. Okay, if we didn't have that cosine of x, then I wouldn't be able to do substitution. Y'all see that? The antiderivative of sine x, we couldn't do. Because although we have a composite function, the derivative of that inner function wouldn't be sitting outside. Okay, but now we can because of that factor. Okay, so just approach this problem like a typical substitution. Let u equal to sine of x. Find du. So this is du dx. I'm already gonna multiply by dx and save me a step. Du is equal to cosine of x dx. Okay, so let's transform the integral. Now, since we are changing from x to u, this is going to be in terms of u here. You do not want to copy these limits of integration down because these limits are in terms of x for this integral. You have to change them, you have to switch them to u. Just like that example from yesterday where we transformed this integral from 2 to 4 to an integral from -1 to 1. We have to switch the limits of integration. Okay, so I'm going to switch those in a second, but please don't copy those down. This would be wrong. Okay. All right, so here I'm going to get sine of, that sine of x inside is just u. And this cosine x dx is just du. Okay, cosine x dx is du. So the antiderivative turns into just the antiderivative of sine of u, an elementary antiderivative. Now transform those limits. Okay, so how do I transform these? Well, you use the relation between u and x. U and x, this relation. Okay, so we say if x is, let's transform the bottom limit of integration, which is 0. If x is equal to 0, then u is equal to sine of 0. Plug your x's in here. Sine of 0. Sine of 0 is also 0. Okay? Now, by coincidence, both x and u are 0. Okay? So this limit is 0. But remember, this is x, this is u. And by coincidence, they're both the same because that happens here. Transform pi over 2. So we say here if x is equal to pi over 2, then u is equal to sine of pi over 2. And that's equal to 1. Okay, so an x of pi over 2 becomes a u of 1. Again, these are x equal to, or x values, these are u values. All right, now our the definite integral is now in terms of u. Our limits of integration are also in terms of u. And we said yesterday that the answer to both of these is the same. They represent the same area, okay? So find the antiderivative of sine of u. That's equal to the negative of cosine of u. And by the way, maybe I should just, let me leave these in blue. Yeah, so cosine of u. And then we're going to evaluate from 0 to 1. Okay? You do not need to change this back to x. That's the good thing about changing the limits of integration is that we don't need to transform this back to x and say negative cosine of sine of x. We don't need to do that. If I did that, if I left this as negative cosine of sine x, if I substitute it back, then I would have to use the original limits of integration, which are 0 to pi over 2. That's what I would have to do if I wanted to change back to x. But since these are in terms of u, so you can just plug those in to your integral that is in terms of u, or antiderivative that is in terms of u. You get negative. You can leave the negative out. Cosine of, plug 1 in, minus cosine of 0. Cosine of 1 is, I don't know what that is. You need a calculator for that, so just leave that alone. Cosine of 0 is 1. That's the answer. You could multiply the negative in if you want. But cosine of 1, this one is not a number that we are familiar with. I mean, we could do cosine of 0, pi over 3, pi over 2, pi over 6. 1 is not a known angle, so leave it. Oh, Saad, sorry, I did not see your question, Saad. Let me answer Carlos's question. What do you mean negative for du, Carlos?
Well, isn't the derivative of sine x negative cosine x?
Oh, no, it's not. It's not. You scared me for a second. The derivative of sine x is positive cosine x. But the derivative, the antiderivative of sine x is negative cosine x. I think you're mixing antiderivative and derivative. The derivative of sine is positive cosine, but the antiderivative of sine is negative cosine, backwards.
Got it.
Mm-hmm. Yeah, yeah. Saad, the answer to your question is yes, absolutely, Saad, because the derivative of b would be 0. Good observation. Okay, so let's do more challenging. Yeah, so please, guys, go make sure you change your limits. Let me get the next problem going, and then we'll take a break. Let's say we have the antiderivative of, let me see. This one is, I'm looking at the problem. The antiderivative, I'll just make something up. The antiderivative of x times the square root of 1 plus x. Okay, so this problem is a little bit more challenging because first of all, we have a composite function, square root of 1 plus x. So that's all right. All good. So let's just do this. If I let u equal to square root of 1 plus x, then du is equal to, so du over dx is just equal to, the derivative of 1 is 0, and the derivative of x is 1. So I multiply by dx, and I get du equal to just dx. Okay, all good. So let's see if substitution works. Okay, this becomes square root, let me rewrite the problem. That becomes the integral of, so here I have square root of u. Okay, great. This dx problem says, my math says dx is equal to du. Okay, so this transforms to du. Okay, great. But I have an x here. What happened to this x? What do I do to that x?
We can consider as a constant or
We
not?
cannot. Definitely not. So if you do this, guys, again, today is the day that tells me if you've been absent or not. Or on the test, if you make this mistake, I will know for sure that today you were absent because you're not here to listen. I'm gonna make a big deal out of this. This antiderivative, if you write your antiderivative like that, this makes absolutely no sense, okay? Because you have an antiderivative that involves a variable x, but the integration is with respect to u. You can't do that. We can't do it. This is a complete nonsense. This says that the variable is gotta be u because it's integration with respect to u. It's differentiation, anti-differentiation with respect to u. Okay, so I can't have that x here. And no, x is not a constant. X is a variable. but it's not the variable of the integral. You should have changed everything. This x is stuck. It's stuck. It just doesn't belong here. It should go. Okay, you know how someone dies and they say their soul is stuck on earth? I heard people say, it's just like that. Their ghost is stuck on earth. Have you seen that movie Ghost? Just like that. This thing is not, it just doesn't belong. It has to transform also. So Carlos, oh, I thought Carlos is answering the question. Who can tell me what to do with this x?
X equal u minus 1.
Yes. Yes. We need to transform everything. Everything. Okay? If you're doing a u sub, the u sub transforms everything from x to u. 1 plus x is u, dx is du. This x, so you ask yourself, how do I express this in terms of u? Well, I look at the relation between u and x right there. This tells me over here that, let's write that in red. It tells me that x is u minus 1. So this type of situation can happen where you have an extra factor that didn't transform directly, but you just have to do a little bit of work to do the transformation for that. So this x is u minus 1. Now our integrand is all in terms of u, and that's how it should be. Okay. So what you want to do is, okay. So I want to do this antiderivative. What I need to do is write it term by term and use the power rule. Okay. So here we have u minus 1, and then that square root of u is the same as u to the half du. I'm just doing the algebra before calculus. Multiply u to the half in, or distribute that in, you get u to the 3/2. I am not doing antiderivative, guys. Just multiplying in, minus u to the half. Now we are ready to find the antiderivative. So add 1 to each power, you get 3/2 plus 2/2, that's 5/2, multiplied by 2/5, minus u to the add 1, 3/2 multiplied by 2/3, plus c, and then substitute back for your u. U is 1 plus x, or x plus 1. So we get 2/5 times 1 plus x, or x plus 1 to the power of 5/2 minus 2/3 times x plus 1, or 1 plus x to the power of 3/2 plus c. So remember, when you do a u sub, every single thing in the integrand as well as the dx must become all in terms of u. So if I were to just leave that x here, the problem is a complete nonsense. Okay? Yeah, you guys go ahead, take a 15-minute break. Please come back at what time? 9. Come back at 9:40. Yeah, 9:40 is good.
Recording in progress.